There's a few other conversions, a few other ways to convert alcohols to good leaving groups. A few other methods, we're just going to put them in the notes. The first two we discussed, using strong acid and then using tosylates, those are the important ones. These ones, a little bit less important. We're not going to talk about the mechanism of these things, but these things show up on standardized exams occasionally, and you might see them in the future in this particular course. I just want to have them in our notes for you for the second half of this course. PBr3 is a reagent that can convert alcohols readily into bromine, and there's a reagent called thionyl chloride. It's SOCl2. It's kind of a funny reagent. It has the ability to convert alcohols into chlorides. So there's ways to directly convert alcohols into these types of leaving groups. The chemistry is not terribly complex. If I showed you the mechanism, you would get it, but there's no need for us to belabor these points, go into detail about them. There are just other methods. There's hundreds of methods, literally, but these are very common methods. Sometimes you'll see them in the textbook later in this course, in the second half, and just want you to have them at your disposal or somewhere in the interstices of your mind. You've seen something like this before. Again, for us, number one most important ones are using a strong acid like HBr or HCl, or tosylates. Those will be the ones that we'll use. I think they're the most important for you to learn about. Okay. So again, this little introduction here, we've been focusing a lot on the leaving group, identifying a bad leaving group as a strong base, thinking about how to transform it. We're going to talk now about a method for making ethers. This is actually named after someone, Williamson. It's called the Williamson ether synthesis. Don't need to know this name, not really so important for us. It's just a SN2 reaction to make ethers. Okay, the goal of it. And so we're just going to review, use this particular special type of synthesis to do a few special things. Let's just put a specific example up here of the Williamson ether synthesis. We're going to take this particular compound, plus methyl iodide. This is called phenoxide. It's the conjugate base of phenol. We actually saw phenoxide and phenol earlier this semester in our acid-base work. We learned a little bit about this particular compound, but it's not playing a role as a base here. Let's look at these two particular reagents and think about what's the substrate, what's the leaving group, what's the nucleophile. Shouldn't take too long to identify this is the substrate. It's methyl. It's the best. We have iodine here. Don't remember if it's a good leaving group or not. If you break this bond, it leaves as I-. You should identify it as a good leaving group. And we have a nucleophile here. O and O- aren't the best nucleophiles, but this should work, or at least we'll try it and see what happens. And SN2 reaction, again, is very, very simple at this point. And this particular reaction allows us to make ethers. I kind of made a little bit of an exotic ether here. It has a benzene ring on it, a methyl group on one side. But this is just a very, very simple reaction called the Williamson ether synthesis. It's a reaction to make ethers. Take a substrate with a good leaving group and attack it with O-, and this works no problem. Again, O- here isn't the leaving group, it's the nucleophile. So, again, forgot to put my I- here, but that's a good leaving group. So this reaction works very, very well to make ethers. I want you to think about this for a minute, looking in the backward direction. This is the bond we made right here. Just going to put a little dot through it. Okay? And I want you to look at the relationship between that bond and all the other components in the reaction. Okay? I want you to look at that bond and think about how we made it. Look very closely at the two things where it came from. Which was the substrate, which was the nucleophile in this pair. The substrate is always attached to a good leaving group. And what would be the best possible nucleophile for oxygen if we want to make an oxygen-carbon bond? Well, it should be O-. I want you to just keep that relationship together. Let's think now about how to make a molecule. The molecule I want us to contemplate here today is this ether here. It's an ethyl isopropyl ether. We could literally call it isopropyl ethyl ether or ethyl isopropyl ether. It has a IUPAC name, which I really don't care about, but we can take the ethyl group, we can take the isopropyl group and say ethyl isopropyl ether, and that's its name for today. It's technically accurate. How do we make this particular molecule using the Williamson ether synthesis? Meaning, how do we make this from simpler molecules? One side of this ether is going to come from a nucleophile, one side is going to come from a substrate. There's actually two possible ways to do this. And what I want you to do is come up with at least one of them right now on your own. And I know this is very difficult if you guys are in your homes. I can't have you work with a friend right now on this very easily. Breakout rooms just doesn't work very quickly for us to do here, given the time. But I want you to come up with two strategies. There's two methods to make this ether. And just think about either breaking for right now, either pick this bond here at the bottom or this bond here at the top. Just pick one of those two, either here or here. And I want you to backtrack using this kind of idea on how we went forward in this direction. So if you pick the top bond and cut it, which half of the molecule is the substrate, which half of the molecule is the nucleophile, just draw them, right? So I want you to draw on some stuff here plus here, and there's two different possibilities for this, here plus here, depending on which of the two bonds you break again. So either pick this bond here, let's call it A, or pick B, that one here, and fill in what reagents, specific best reagents you would want to use to make this particular molecule. If I said, please make this molecule for me using a Williamson ether synthesis, using compounds that contain 3 or less carbons, what were the two building blocks you want to come up with? Please sketch something. Do your best. Don't sit here and stare off at something. Don't flip through your notes. Everything you need is on this piece of paper. So just sketch parts of the answer. And if you are partially successful, for me, that's a success. If you're greatly successful, that's also success. If you leave nothing there, for me, that means maybe I'm not doing the best I can to encourage you. So please draw something. By all means, if you want, draw both answers. Think about both of them. I'll give you about 10 more seconds to work on this. Just try and sketch some things. What substrate would you want if you broke bond A or bond B? So when I ask you this question in the real world, I'm not going to put these little cuts on these bonds for you. I'm simply going to give you the parts written in blue here and ask you to come up with a way to make this particular molecule. So today, we're just thinking backwards. How do we make this using SN2 chemistry? Well, we need a substrate, we need a nucleophile. Let's imagine cutting at bond A. Cutting at bond A. Following the logic here, the carbon side of this cut is from our substrate. And I would want an ethyl substrate, and you should put a leaving group on it too. I'm going to put iodine. All right, why not? Put bromine, that's fine. Put chlorine, that's fine. You can put tosylate. Those are all fine answers. They would all work equally well for us. The other side of the equation, you need to have a nucleophile that has oxygen in it, and it has all these carbons attached to it. This would be isopropoxide, and to be perfectly technically accurate, we would write sodium next to it. But if you simply wrote this particular fragment here, that would be enough for me. If you wrote isopropanol there, intellectually that's on the right track. If this was an alcohol, it could act as a nucleophile, but alcohols aren't really that good of a nucleophile because oxygen's electronegative. On the other hand, if we make it negatively charged, we enhance the nucleophilicity of oxygen. So this would be the best possibility. Okay, so this is one possible way forward. The other possibility, some people I'm sure got this, they do every semester, is we cut at bond B, and things are going to switch around. The substrate is going to be the carbon bit at the bottom, the nucleophile will be the oxygen bit at the top, and so the substrate we would have here is an isopropyl group. To make it a best possible reaction, why don't we put a good leaving group on it like iodine? Okay? And then the nucleophile, right? If you didn't do this part, what would the nucleophile be if we cut bond B to make this molecule in the forward direction? Well, it should be ethoxide. All right, it could be sodium ethoxide if we wanted, potassium, lithium, those things don't matter. Okay, so these are two possible syntheses to make this particular ether. There's two ways because there's two different bonds we could approach. I want you both to evaluate these reactions in the forward direction using everything we know about leaving groups, substrate, nucleophile. Which of these reactions is actually better to make this as the major product? Or which one of these reactions would happen faster? Think about that, and then please just write an answer either to me or everyone, doesn't matter. Which one is better and why you think that's the case? Which one of these would give ethyl isopropyl ether either in higher yield, do you think, or would occur faster or more easily? So pick either choice A or choice B and give a brief reason for it. Maybe it's the leaving group, maybe it's the nucleophile, maybe it's substrate, maybe it's something else. So by all means, just type in. If you're too shy, type it privately to me. If you're brave enough, type it to everyone. We're all learning together here, so really, even wrong answers we can all learn from. That's not the point. No reason to be shy about these. So either A is better or B is better. Once you have an answer, share it with everyone, please. Okay, A, good. Now we need a reason why A. Just write something short. Why do you think A is better? Just put it in a brief half sentence. Substrate is primary. Great. Thanks, everyone. Wonderful. Right. So if we were evaluating these reactions side by side, right, which one of them would be faster? Which one of them would be better? Well, nucleophile has different shapes and sizes on it, but that doesn't matter for the nucleophile. The nucleophile, both of them have O-, so that's the same, okay? Iodine, same leaving group. So the only thing that's different is the substrate here. This is a primary substrate. This is a secondary substrate. This would be the better choice. So you can see how this would be a nice little question I could ask if I really wanted to test how deep your knowledge is of this. On a surface level, I could ask you, well, provide one synthetic way to make this from simpler reagents using an SN2 reaction. Or I could say, provide both possible ways of making this using an SN2 reaction, and then carefully examine your two possible ways, which one would be better. That's kind of a difficult question to ask in a summer course like this, but that's the level of mastery you should aim for with these types of problems. And this type of problem is very similar to the Diels-Alder reactions we were doing recently, where we would draw a product and I'd say, well, how would we make this from a diene and an alkene? So thinking backwards in organic chemistry is important. It's the hardest thing we do as chemists, is to make something and think what's the best way to make it. But for this particular reaction, I want us to have that kind of tool and set of skills. I want you to work on them just a little bit, okay? Obviously, I recognize this course is fast. We're learning a lot for SN2, but for this particular type of reaction, the Williamson ether synthesis, work towards this level of understanding. So happy you guys chimed in so quickly. So many great answers. I see you're following along great and thinking you're right where you need to be in this course and this lecture. So thank you.